Okay, we are recording. It is Friday. We are live. Let's get started. Welcome to structural analysis again. Hope everybody's doing all right. Little gray outside. Looks like it might rain again, so hopefully everybody stays dry today. Couple quick announcements. So the homework again, we're same schedule. You all turned in the homework assignment. The one on Wednesday, that's been graded and the solutions posted. Homework 2.3 was due right before class, and then homework 2.4 is going to be assigned after class. Now, because of the weekend, because of the holiday, homework 2.4 isn't going to be due until Wednesday, so I'm not going to make you have anything due during the holiday. Another point I'll mention, and I don't know, it's probably more me than it is Blackboard, but I had a couple issues with Blackboard. The solution, I had a student instructors email me that the solution was only showing the first page, so I refreshed it. In mathematics, there was a student who submitted their homework assignment, but from my end, it looked like they hadn't. I had to actually dig into the grade center to find their solution. I guess my overall point is if you all have any bugs or any glitches, don't hesitate to let me know. That's what I'm here for. So yeah, it's been a little frustrating that you upload everything and then it didn't work. I don't know. It's just because everybody's using it that the system's taking a little while to catch up. I'm not sure. But unless everybody has any questions, we'll get right into it. Today, what we're going to do is we're going to talk about the last topic associated with reactions, and that's the presence of an internal hinge. That's something we haven't dealt with, and it's gonna seem to amp up the complication. It's really not, but we're going to have to use a tool we haven't used yet, which is cutting a section. So let's just recap where we're at. So up until now, like I said, we've been working on support reactions, and we've assessed a number of conditions. I mean, just take a look at this slide, and look at all we've dealt with. We've dealt with concentrated loads. We've dealt with distributed loads. The uniformly distributed loads, triangular distributed loads. We've dealt with inclined loads. We've dealt with inclined supports, concentrated moments, fixed supports, pin boundary conditions, rollers. We've dealt with a lot in just the past few lectures, and so hopefully what we've done over the past few lectures, and hopefully I think you'll see that's kind of the spirit of this class, is that we take some of the critical principles in statics and we present them in a little bit of a different way, but we use those tools to assess more complicated structures. And really the point is they're not all that complicated. They're just maybe a bit bigger and just a little bit more going on. But hopefully you sort of to get the picture on that. We've got one other thing that we need to discuss, and that's an internal release. And so an internal release is basically a point in the structure where the response, a particular response, has been relieved. And so you can have a shear release, you could have an axial release. The most common release that we use is a moment release or a hinge. And we've mentioned hinges before, but we haven't really dealt with them yet. I want to say a couple of things about hinges. You do find physical examples of them in the real world. The image on the top right, that is a pin and hanger connection. You'll find that in a lot of older bridges, and those connections transfer, shear and axial load, but not moment. And then also maybe a more modern example is something you might see here on the bottom. If you have a beam connection in a building, and the web is connected but not the flanges, so that image on the bottom, you can see the center portion of the I-beam is connected but not the flanges. That connection has been designed to only transfer shear, not moment. So analytically, we would treat that as a hinge because it doesn't have the oomph necessary to resist those moments. Most of the moment in a beam is carried in the flanges. Now, in order to assess a structure with a hinge on it, we have to be able to employ the secret weapon of structural engineering. And the secret weapon of structural engineering is a samurai sword or a lightsaber if you happen to be a sci-fi fan. What am I talking about? I'm talking about cutting a section. Okay, so here's the thing. Cutting a section is one of the most important analytical tools that we utilize as civil and structural engineers. When we cut a section, we can use that to validate our answers. So, when we're doing a problem, let's say we're drawing our shear diagram and we're drawing our moment diagram, and let's say we look at the shear diagram and we look at a particular point on the beam and we get that the shear is 30 kips. So at that particular point, so we should be able to cut a section and use equilibrium and verify that the shear is in fact 30 kips at that particular point. And with that, we can use the tool of cutting a section to determine those internal forces, determine the axial forces, determine the shears, determine the moments. Another big one is we can use it to determine moment and shear functions. So instead of just a moment value, like an equation for moment, so moment as a function of x or shear as a function of x. And that's really important later on when we are looking at deflection. So we're going to need to be able to assess that later. And so there's a number of different uses for this tool, and we're going to be using it quite a bit throughout the semester, so I kind of want to explore it. And so I mentioned this example a few days ago, but here I've got this bench and I've got somebody sitting on a bench, and you come out with your samurai sword or your lightsaber, depending upon what you choose to use, and you cut right through the bench. Okay, now if I'm sitting on this bench, what's going to happen is I'm going to fall down. Okay, by cutting the section, by actually separating the bench into two separate pieces, what I've done is I've removed from the bench the ability to resist the forces at that location. And so I've sort of split the bench, if you will, into two separate pieces. Maybe I'll add some three-dimensionality to it so you can kind of see three dimensions. So I've taken the bench and I've cut it into two separate pieces. Just looking at this system as it is, if that's my bench, I'm going to fall down if I sit on that. And the reason I'm going to fall down is because inside the bench there were forces, there was a response inside that bench that kept it upright at that particular location. And you can use equations of equilibrium to determine, well, what is the response inside the bench at that location if I were to cut a section. And so let's take a look at that. So if I have a structure and I cut a section, what happens? So let's take a look at this next slide and let's sort of digest it for a bit. I want to leave it on here for a second. So I have here an image of just some arbitrary structure on the top, okay? And so imagine that that's the bench, okay? And so I've got this structure. Let's take that structure and cut it with my samurai sword or lightsaber, whatever tool you want to use. And let's cut it and let's separate it into two pieces, okay? And so I look at the left or I look at the right, and I try to determine, well, what are the internal forces that can be present? Well, first thing to keep in mind is that if we're looking at a two-dimensional structure, whenever I cut, through some arbitrary point, I've got the bench and I chop through the bench, I have at most three unknown forces, like an unknown force in the x direction, an unknown force in the y direction, and an unknown moment. It corresponds with my three equations of equilibrium: sum of forces in the x direction, sum of forces in the y direction, and sum of moments. But what happens when you cut through a hinge, remember, a hinge is a moment release, okay? So if I cut a section through a hinge, I can still have an axial load and I can still have a shear, but I'm not going to have a moment. And that's what makes a hinge so special. Whenever you cut through the hinge, you know that the internal moment is zero, okay? Now, that's probably the first thing that you notice. The second thing that you notice is that the image kind of looks a little complicated. I got, a V going up, a V going down, P's and moments, and what's going on with either side, okay? Well, first off, this goes back to, some of those Newton's laws, equal and opposite. Whenever you cut a section, you generate responses on either side of the cut that are equal in magnitude but opposite in direction, okay? And so let's take, for instance, the axial forces P on the bottom left, okay? When I cut a section and I look at the internal forces, on one side, I'm going to have a force going one way, and on the other side, I'm going to have a force of equal magnitude but going in the opposite direction, okay? And so, those two forces, so for instance, I've got the forces, they're sort of pointing inward. They're either both going to be pointing inward or they're both going to be pointing outward. Again, they're equal in magnitude but opposite in direction, okay? And so what that means is we kind of have to adopt a sign convention. Now, I'll go ahead and tell you that this sign convention for what we're doing right now with reactions really isn't going to matter. This is going to become more important later when we look at trusses. Like, it's going to kind of become important when we look at trusses, but it's going to become really important when we look at shear and moment diagrams. For now, not that big of a deal. It's just something, an idea I want to introduce. Okay. So for the sake of discussion, let's look at the positive axial forces. Okay. What I'm proposing is that when we perform calculations, not just in this class, but in civil engineering context, typically what we do is when we look at axial forces, we assume that this is positive. So the axial force is pointing inward. Think of it like this way. So if I cut a section and I look at either side of the section, I'm going to draw the arrow pointing away from the member. The idea is that a positive axial force yanks on the member. It applies tension, so it makes the member longer. So if I had an axial force that was negative, it would just be pushing towards the member. It would be pushing, that way. And so that's just the sign convention that we adopt. There's nothing necessarily right or wrong about this sign convention. We could just say, you know what, we're just going to use the other one. We're going to say that the positive axial forces push towards the member. There's nothing right or wrong about it. We just sort of have to pick one. And what I'm saying is that the sign conventions that are shown here, the conventional sign conventions that we use in civil engineering context. So for instance, if you're looking at shears, when you cut a section, look to the left, positive shear force goes down. Look to the right, positive shear force goes up. When you're looking at bending moments, cut a section, looking to the left, you've got counterclockwise moments that are positive. Look to the right, you have clockwise moments that are positive. One of the things I'm sort of, a term that I'm throwing out is this whole look to the left and look to the right. The actual direction in which you look doesn't really matter from a computations perspective. In other words, keep in mind that the forces are equal in magnitude. They're opposite in direction, but they're equal in magnitude. So if I'm looking at my axial forces and I get 20 kips on one side of the section, I'm going to get 20 kips on the other side of the section. It's just going to be in the opposite direction. So what that means is that when we're actually doing problems and we're cutting sections, what we do is we look at it strategically and we ask ourselves, what's the easiest thing to do? And that's generally what we employ. Again, don't try and make the problem harder than it needs to be. And usually when you cut a section, you can look at it and see this is the way I kind of need to cut that section. Any questions before we get into our reactions example? And we only have one example today. This example is going to take a little bit longer than the examples we've done in the past. One of the things I will tell you is that when you're looking at a structural analysis problem that involves an internal hinge, there is a good chance it will take a little bit longer. So your homework assignment only has one problem, and we're only going to do one problem in class today. I'm going to erase the bench at this point because I don't really need that. Any questions? While you're doing that, I'm going to pull up the notebook.
So far, so good.
Good deal. All right, let me pull up the notebook, and you all can copy this problem down. Let me, come on. It's deciding to take its time to load while that loads up. Come on. Stop this share. All right. Come on. There we go. All right. Library, example. Okay. So here's our problem. Let me see if I can move this maybe a little bit. Oh, goodness. Let's do that. Give us a little bit of room here. Okay, let me lay my screen down. Okay, so here's the beam, and I decided to, I don't want to say make the beam involved, but I wanted to throw some distributed loads, some triangular loads, a bunch of different things on this problem to just sort of emphasize that this problem may look nasty and it may look like there's a lot going on, but there really isn't. In the end, this problem is no more complicated than any of the other problems we've done in the past, barring the presence of this hinge. And so let's look at this in a bit of context. Okay, first thing I'm going to do is I'm going to look at my support reactions. I have now here, we don't have 3 support reactions like we've done in previous problems. We're going to have 4, okay, because we're going to have a reaction here. We'll call that AY. We're going to have a reaction here. We're going to call this BY. Then we're going to have a reaction here. We're going to call this CY. So now we've got 3 vertical reactions and 1 horizontal. Now, the horizontal one, we can, go ahead and, utilize, sum of forces in the x direction to indicate that AX is 0. Like, that's fine. We can go ahead and explore that, or exploit that expression now. And we can just state that AX is 0. We can just get that out of the way. But that's not going to make solving for any of the other ones any easier or harder. Now, I want to go ahead and start dealing with the distributed loads. Let's go ahead and do that now. So let's just take those one at a time. So starting over here on the left, I have 2 kips per foot over a distance of 15 feet. So I'm going to say that's 30 kips, and I'm going to indicate that as 7.5 feet, 7.5 feet. Got my 14 kips, and I'll go ahead and walk us through the others because I think hopefully by now the distributed load stuff, I don't want to, one of the things I don't want to do is I don't want to, just start skipping through steps. If you need me to take a step back and explain something, don't hesitate. But for instance, later on in the semester, I might just start, the reaction is 12 kips instead of going through the process of actually computing it because we've had so much practice on it. So if I ever am going a little fast, don't hesitate. Don't stop me and say, or don't hesitate to stop me and say, hey, where'd you get that value? All right. The distributed, so let's go to the triangular load. So we have 4 kips per foot, linearly distributed over a distance of 15 feet. And so that makes this 30 kips. And, this is a triangular load. So this is 5 feet, this is 10 feet. And then we have our distributed load here, 1.2 kips per foot over a distance of 15 feet. 1.2 times 5 is 18. And then this is 7.5 feet, 7.5 feet. So it's like before we do any of the analysis, let's take a second and break down the problem. All right, I'll give everybody a sec to copy this down, and then we'll get into the numbers here in a bit. And if you're wondering, here on the camera, this is just that beam. I just redrew it because later on I'm going to make a point about this. I guess the other, maybe if we want to go ahead and eat something, make sure that everybody recognizes that is the hinge. So this problem has an internal hinge between B and C right in the middle there, right where this triangular load and this uniformly distributed load meet. So maybe I'll fill that in here. Or do that. Okay, everybody good? All right, and like I said, if you ever need me to, somebody have a question?
I just said yes, so you're good.
Oh, okay. If you ever need me to go back or whatnot, just let me know. Okay, so what I want to do is I want to handle this problem like I would any any problem that we would do in this class. So I want to look at this problem and I want to say, let's just handle it like we did before. And so, to try and adopt that same approach. So let's just sum moments at A and see what happens. So let's sum moments at A. Let's just see what happens. Now, this one's going to be kind of involved. There's going to be a lot of different pieces. So, tell you what, actually, let me move this over. I want to give myself a little bit more room. There we go. In fact, maybe I'll scroll down a bit. Makes it a little easier to write. There we go. Okay. So we're going to start at the left, work our way over to the right. So we don't have to consider the AX. We don't have to consider the AY. We do have so let's make sure we count all of our loads. We have the 30 kips at a moment arm of 7.5 feet. And then we got that 14 kips at a moment arm of 15 feet. So 30, 7.5, and then we have 14 times 15. All right. Moving on, left or right, we have the BY. BY is a moment arm of 30 feet, and so we put that over here. And then we have next the triangular load, so we've got that 30 kips per foot. And let's involve y'all a bit. What's that moment arm for that triangular load? For this one right here, what's the moment arm? $35, exactly right. Pull the chat back up. All right, 35. Good deal. All right. Now, question, do we do anything with the hinge right now? The answer, no. The hinge, this isn't some external load on the structure. It's just a point on the structure that we know something about. So we don't do anything with the hinge. It's not an external load. Okay. Lastly, we got the 18 kips this way. And what's that arm? Somebody tell me in chat.
$52.5.
Exactly right. 52.5 feet. And then, but is there something I'm forgetting? Did I miss one? Yeah, the CY. So we've got the CY, and that one's going to be at a moment arm of, what, 15, 30, 45, 60 feet. Okay? And that makes things a little weird. Okay? Because what happens is, so let's do the math on the left. So I've got 30 times 7.5, that's 225. 14 times 15, that's 210. I got 30 times 35, that's 1050. And then I got 18 times 52.5, that's 945. All right, so, 225 plus 210 plus 1050 plus 945, I get 2,430 foot kips equals, and what does that equal? It equals BY times 30 feet plus CY times 60 feet. Huh. See, it didn't give me an answer, right? I don't get, BY equals 12 kips or CY equals 52 kips. I get this equation. In fact, I'm going to take this equation, I'm going to write it on the board. I'm going to copy it. So I've got, let's put it here, BY times 30 feet plus CY times 60 feet is 2430 foot kips. So I didn't get an answer. I got an equation. Let's call this equation 1. All right. So it's not an answer, but it's something. So maybe I'll box that here on the screen. It is a fact that, The structure must, the reactions must, conform with this equation. Otherwise, the structure won't be in static equilibrium, but it's not an individual reaction. All right. Let's try. Let's keep going. What about sum of forces in the y direction? What happens there? Are we going to get anything different? Well, what do we have? We've got, let's look at the structure. Let's start from the left to the right. So we have AY going up. We have 30 kips going down, 14 kips going down, BY going up, 30 kips going up, 18 kips going down, CY going down. AY plus BY plus CY equals, what do we got? We got 30 and 30 is 60, 14 and 18 is 32, so that's 92 kips. Huh. Now I'm even more lost because I've got AY plus BY plus CY equals 92 kips. Okay. That's equation 2. Let's go ahead and circle that one as equation 2. All right. I can do a little better than that. I'll give everybody a sec to copy this down and catch up, but I want you to sort of think about what's going on. We have 3 equations of equilibrium. We have the sum of forces in the x direction, we have the sum of forces in the y direction, we have the sum of moments. Now let's take each one of those one at a time. Sum of forces in the x direction we've already used. That gave us the AX reaction. Sum of forces in the y direction gave us equation 2, and sum of moments gave us equation 1. And we're still no closer to solving any one of those independent reactions. So what do? Well, we have to know another fact about the structure. Okay, we have to know another fact. If that hinge didn't exist, this would be an indeterminate problem, and we'd have to, that would be much more involved, and we'll talk about that later on in the semester. But I want to go back to this notion of stability and determinacy. If I was trying to compute the IE value for this structure, what would I say? Well, how many reactions are there? 1, 2, 3, 4. There's 4 reactions, so R is 4. But what about E sub C? What would the E sub C value be? The E sub C value is 1. Why is it 1? Because we have a hinge. But let's go back to E sub C. What does E sub C stand for? It stands for equation of condition. That hinge tells us something about the structure. It tells us our 4th equation, our 4th fact. It tells us that the sum of moments at that hinge is 0. Okay? So let's go back to this a bit. Okay? So here's our structure. Here's the structure. We have equation 1, equation 2, but we have yet to utilize this hinge. I propose that we break out that secret weapon of structural engineering, samurai sword or lightsaber if you happen to be a sci-fi fan. And we take this hinge, we cut the structure right here. Maybe if you're an Evil Dead fan, use a chainsaw or something. Okay, so we have our structure right here, and we cut a section through the hinge. Okay, now what that's going to do is it's going to separate the structure into 2 pieces. Okay, so you're going to have this piece of the structure, and you're going to have this piece of the structure. And what you have to do is you have to ask yourself, okay, here's my structure. I'm cutting a section at the hinge. Remember, statics doesn't care. I can look to the left or look to the right. It doesn't matter. I'm going to get the same answer. So then we talk about strategy. Do I look left or do I look right? And I don't know about you, but there looks like there's a whole lot less going on over here on the right than there is on the left. So instead of dealing with all this hullabaloo over here on the left, I'm just going to look at this stuff on the right. So what am I going to do for my tool? I'm going to cut a section. I'm going to look to the right, and I'm going to investigate this part of the structure right here. So I'm going to focus my analysis right there. Okay. So let's go back to the screen or to the notebook. Let's scroll down a little bit. Let's see what this looks like. So let's cut a section at the hinge, and let's look to the right. And what does that look like? Well, go back to the, if you need to hop back and forth between the, oh goodness. If you need to hop back and forth between the screen and the camera, go right ahead. But all I'm going to do is just draw the structure, everything to the right of my cut. Just everything over here. So what do I have? I've got, this. I have my roller here. I'm going to have a reaction there, but I don't know what that is yet. Haven't figured that out. I've got my section cut. I cut right there. See, I've got my load. And that's 1.2 kips per foot. Let me lower this just a little bit. There we go. Let's lower that just a little bit. Okay. Now, remember, I cut through a hinge, okay? So whenever you cut through a hinge, there is maybe an unknown vertical force. Maybe we'll call that, I don't know, Fy. And there's an unknown horizontal force, Fx. But to be honest, as we're going to see here in a second, it doesn't really matter what those forces are because we don't really care if all we're determining is the reactions. Last thing we need some dimensions. So this is 15 feet. And maybe we'll go ahead and do this part. We said that was 18 kips, and this was 7.5 feet. Okay, I'm going to give everybody a sec to copy that image down, and then we'll talk about how we're going to go about this. All right, I'm going to assume everybody's good on the copying. And again, if you need more time, just let me know. All right, so here's the thing. We cut a section at the hinge. We look to the right, and so that's everything on the structure to the right of that section cut. Now, when we cut the section, we know, or when we cut at the hinge, we know there's an unknown force in the x direction, and we know there's an unknown force in the y direction. But we also know that the sum of moments is 0. And so what I'm going to do is I'm going to sum moments. I'm going to say sum moments, and we're going to say sum moments at the hinge. Maybe what we'll do is we'll say sum moments at the hinge looking right is 0. And so I'm going to sum moments at the hinge just like I would sum moments, to determine a reaction, just like I would any other problem. And I'm going to ask myself, I can make that a little shorter probably. What's going on with this structure? Well, sum moments at the hinge. Do I have to consider my Fx? Well, no. That goes right through the hinge. That's why it doesn't really matter what those values are, because when we sum moments at the hinge, we're not going to have to worry about them. So the Fy goes right through the hinge. The Fx goes right through the hinge. The only thing I have to consider is the fact that I've got 18 kips acting at a moment arm of 7.5 feet. I got a Cy acting at a moment arm of 15 feet. Therefore, what is 18 times 7.5? That's 135 foot kips is Cy times 15 feet. And so CY, or 135 divide both sides by 15, 135 divided by 15 is 9. Oh. Does that make sense? Does anybody have any questions on that? I know I hope I didn't go through that too quickly. I'll give everybody a second on that. All right, let's go back to the board, the whiteboard for a second. I want to take a look at this from a little bit of a bigger picture. Okay, so here's my structure, and I still got this equation 1 and this equation 2 I haven't dealt with, but what do I now know? Well, I now know that. That's one of my answers. Well, if I know that, what do I do? I'm going to ask you. I'm going to ask the chat or somebody with their microphone. Tell me, what do I do? If I know this, what do I do moving forward?
You just plug it in for CY.
Exactly right. And then what's that going to give me? That's going to give me BY. And if I know BY and I know CY, plug it in here to get AY. All right? And that's it. So it's actually pretty simple. So I guess my overall point with this lecture is I don't want you to think that an internal hinge makes things more complicated, even when you start applying your equations of equilibrium and you get, this, and you're like, oh God, what do I do here? No, just cut a section, and once you get your value, start plugging and chugging. Pretty straightforward. So let's go back to the screen share. There needs to be a short button for that. I have to go through all these menus to do the sharing. Okay. So what do? We say, equation 1. And so what was equation 1? It was 2,430 foot kips. It is BY times 30 feet plus CY times 60 feet. So 2,430 foot kips is BY times 30 feet plus positive 9 kips times 60 feet. See, sometimes whenever you're doing a reactions problem, sometimes what's easier is, let's say you got a bunch of vertical reactions. Just assume that they're all upwards, every one of them. And then by assuming that they're all upwards, what you could do is just, it makes it easier to keep track of the value. So if you get a negative reaction, just keep it negative. And then once you get all the reactions at the end, then start redrawing your arrows and whatnot. And so that could be a strategy to make it pretty easy. All right, so I'm curious, what's chat getting for BY? Because at this point, you should be able to just solve for BY. I'm going to put this to you.
I'm going to get my calculator out.
You came to engineering class and you didn't have your calculator. My goodness. There you go. That's right. 63 kips. So positive 63 kips. 63 kips going upwards. Because remember, we drew BY acting upwards. We drew all of our reactions acting upwards. And so now what we can do is go to equation 2. And we can say, okay, what is equation 2? AY plus BY plus CY is 92 kips. Hold on.
Now, this one I can do in my head.
Yep, 20 kips, yeah, because you're going to have AY plus, and then this is positive 63 kips, and then plus 9 kips is 92 kips. And so 63 plus 9 is 72, so therefore AY is positive 20 kips. 20 kips upwards. And so, especially with hinge problems, I think it's not a bad idea to, make sure that you're good on your reactions. So, what did this problem have? This problem had 4 reactions. We had an AX, AY, BY, and CY. And so AX was 0, AY was 20 kips upwards, BY was 63 kips upwards, CY is 9 kips upwards. I'm going to give everybody a sec to copy all that down. While you are doing that, let me pull something up real quick. I'm going to make sure I get my problem right. I think it was 34. Okay. All right, any questions? All right, while you all are, and I can go back to the slides, but while you all are doing that, I want to pull something up. Okay, here we go. All right. Well, first off, does anybody need me to go back to the notes? All right, we'll take that as a no. Here's your homework problem. This is problem 334 in the book. Somewhat similar, except for the fact that it's a frame, and so there's a little bit more, two-dimensionality to it. I guess all I'll say about it is this problem is really not all that different from the problem that we just did in class, other than the fact that when you're summing your moments and you're doing your force analysis, make sure that you're accounting for everything when you sum your moments and sum your forces, because there's the 25 kip load acting to the right, but then there's the 2 kips per foot acting downward, and then you got this hydrostatic triangular load acting to the left. So make sure that you handle that. This is definitely one of those problems also where you could just assume that like all your reactions act upwards and all your reactions act to the right, and then if you get a negative answer, it's okay. That means they act downwards or they act to the left. This is definitely a prime candidate for that type of analysis. Any questions about this or the problem that we did? Do you need me to go back to anything? Any questions you got? I mean, please, floor is yours. All right. Well, we're ending 5 minutes early. So first off, I wish everybody has a wonderful weekend, or a wonderful 3-day weekend, I should say. We're not going to see each other until Wednesday. But when we come back, what we're going to do is we're going to begin our next module of the class. So we pretty much handled reactions. We're going to talk about trusses. So get ready for some truss analysis when we come back. That's all I have, everybody. Everybody have a great 3-day weekend. We'll see you on Wednesday.